total Hamming distance. So the Hamming distance between two integers is the number of positions at which the corresponding bits are different. So let's try to use an example. So we're gonna try to use the first example, 4, 14, and 2. So for number 4, so the result is 0, 1, 0, 0, 0, 1, 0, 0, and for the number 14, it is 1, 1, 1, 0. So what is the Hamming distance? So for each bit, each position, if it is the same, so the distance is 0. If it is different, the distance is 1. Yeah. So according to this, at this position, and yeah, let me draw it. So at this position, this is 1, 0. At this position, this is 1, 0. So the distance is 2. Yeah, and we need to check all the pairs, and we need to sum up with all the pairs. Yeah, if we are solving the problem, we need to turn it into a 0, 1 bit, into a binary bit. Normally, this is the bit manipulation problem. Yeah. Now let's try to finish this number 2. It's gonna be 0, 0, 1, 0. So if it is like this, so how can we compare? And how can we compare with each other, and how can we get the result? If we use the brute force, it's gonna be n squared times 32. Definitely, I think it's gonna be time limit exceeded, but I will not use it that way. So we can try to use some other ways to solve it. Normally, we're gonna list all the numbers because this is easier to check. So why not we just check each bit instead of checking the numbers one by one? So for example, let's just check the last bit. Yeah, we will not consider other bit. We will just check the last bit. So the last bit is 0, 1, and 0. So how many? So what about we only check the last bit? So how many of them? Just ignore the others. Yeah, just ignore these areas. We only consider this is 0, 1, 0. So how many different pairs? So 0, 1, 0, 1, only 2 pairs. And this is 0, 0, it's the same. So the result is 2. Yeah, so the conclusion is that why not we just check all the bits? And how many bits of them? I believe it is 32 if the integer is 10 to the power of 9. If it is less than and equal to 10 to the power of 9, basically 32 is enough for us to check the result. So we're going to check each of the bits, and we're going to check how many zeros and how many ones. So for the first example, there are 2 zeros and only 1 1. So it means 2 times 1, there will be 2 different combinations. Yeah. Maybe you don't believe it. Let's try to use another example. Maybe we have another number, maybe 15. So for the number 15, so the result is going to be 1, 1, 1, 1. Yeah. So why not we just check this one? So we have how many zeros for this at this position? There are 2 zeros and 2 ones. So how many pairs? There are 4 pairs, because this 0 can combine with this one and this one. This 0 can combine with this one and this one. So there are 4 pairs. So in this way, we can check the result. We're going to compare each of the bits, and there are 32 bits, and then we're going to check the length of the numbers. So the length of the numbers is 10 to the power of 4. So this will be the final time complexity, 32 times 10 to the power of 4. Yeah, if we use the n squared times 32, it will be the brute force. It will be time limit exceeded. Now let's try to solve it in this way. We're gonna need the length of the nums, definitely, and we need a counter or dictionary. It depends on you. So we need a counter to check each of the bit positions. It's gonna be from 0 to 31, and we're gonna check how many of them. We only need to count 1 or 0. Maybe we just need, let's just count with 1, and how many ones, and n minus the number of ones, it's gonna be how many zeros. So it's gonna be easy. Now let's just check the nums one by one. So for num in nums, and then so here for the bit manipulation, I would like to use some kind of libraries. So the let's use a B. For the B, it's a string. It's a 32-bit string. So I'm gonna use the B. I'm gonna turn it into a string, and inside I'm gonna have the num, and I will take out the string representation. So I'm gonna take out the first 2 characters, Yeah, and then I'm gonna fill zeros. Yeah, and I just wanted to keep it 32 bits. So because it is 10 to the power of 9, so the 32 bits is enough for us, because here said the input will be 32-bit integer, so that means it is okay. Now we can check one by one. So for I, we enumerate this string of b. Yeah, maybe we can use a string, binary string. So let's use s. Yeah, so for IV, enumerate it, we're gonna check this v. Maybe we're gonna use the character c. We're gonna check this character. So if this character is 1, we're gonna use the counter. So the counter of the bit position, it is I. So the plus equal to 1. Now we have the result. Let me just print out this dictionary. You're gonna check what it looks like. Yeah. So inside of the dictionary, as you can see that the 29 bits position it is 2, 30 bits it is 2, 28 bits it is 1. It is okay because we don't need to check the real numbers. We just check the bit at each of the bit. Yeah. So at this bit, it means there are 2 1s, and how many zeros? There's only 1 0, because in total there are 3 numbers, and for this number. Yeah. Now we can get the result. So let's just check the result. So I'm going to prepare a result. So for v in d.values, so inside of the values, I can plus equal to this v times the total number n minus v. And finally, I can return the result. So this is going to be the entire code, as you can see. Yeah, it is not so long. Everything should be clear if we understand how to use the bit manipulation to solve the problem. Now let me submit it to check if it can pass. Now, as you can see, it passed. And why it is so slow? I think it is because we didn't use the bit manipulation. We just use simulated as a method of this bin. So this, I think, is yeah, I think because of this, we slow. Yeah, the speed is not so fast. But the time complexity, as you can see from here, it is n times 32. And actually for this is also 32. Yeah, so for 32 times n time complexity, it is okay for the problem. Thank you for watching. See you next time.